Hello, friends. So let's start our discussion about the next topic that is about phase diagram. So last class we have seen what is this phase diagram, what are the different types and all. So here we will try to understand further more with one few examples in each case. Okay, so when it comes to binary alloy phases, like what we have discussed previously, we have unary, binary, ternary, but in our curriculum or in our discussion, we will be focusing only on the binary phase diagrams. So when it comes to binary phase diagrams, there are two entities, the solid A, solid B. You have two entities. When we take these two entities, there is a possibility that these two entities may be soluble at a liquid state. That means when they are at the liquid molten stage, solid A, solid B, both may be combined and then form a single phase at the liquid phase. Or there can be a possibility where in the liquid state it is soluble, but when it comes to solid state, there may be completely soluble, partially soluble, or completely insoluble in each other. These are the possibilities. Similarly, in the liquid state it is soluble, but in the solid state you may have again these type of variations present. So this is how we are going to classify different types of binary alloy phases. So the same is being represented here, but those which are very important are only stated here, the others are neglected. For example, if you see in this case, we have in the binary phase alloy, you have components completely soluble in the liquid state and completely soluble even in the solid state. So liquid completely soluble, solid completely soluble. This is type 1, which is nothing but isomorphous system. And in the second type, you have two components completely soluble in the liquid state and insoluble in the solid state, which is called eutectic reaction. There is a third category wherein two components are completely soluble in the liquid state but partially soluble in the solid state, which is called partial eutectic system. And there is a variation of type 1, which is called congruent melting intermediate phase alloy. And then we have peritectic reaction, which is again, you have a reaction between liquid and the solid to give rise to a new solid. And then you also have a type wherein partially soluble in the liquid state itself, and then it completely insoluble in both liquid and solid phase. This is about the different type in the liquid. But when solidification takes place, when I say it is a freezing temperature, it is a solid, then even if, though it has converted into solid phase, there is a possibility that it can further have certain transitions taking place or transformations taking place. So that is also we will classify. And one important transformation is about the allotropic change. This is nothing but when an metal exhibits different crystal structures at different temperatures, that is called allotropy. And then we have order disorder anyhow, and you can see that there is a similar name called eutectoid and peritectoid. So what we have seen here is eutectic, partial eutectic. So in the eutectic reaction, it is soluble in the liquid state but insoluble in the solid state. In the same way, there can be a eutectoid reaction. So it is ending with the tick. That means liquid gives rise to two new solids, whereas in the eutectoid, solid will give rise to two new solids. So we are going to discuss them in further, so you will have more clarity when I draw the phase diagrams. Similar sense, you also have peritectoid, very similar to peritectic reaction, which is nothing but liquid reacts with the newly solid to give rise to a new solid. So that is called peritectic reaction. Here, two solids will react and give rise to a solid, that is called peritectoid reaction. So I understand there can be some confusion between the terms and also what is all this reactions and all. But as and when we dive into the formation of the phase diagrams and the reactions, then it becomes much easy for us. So for the time being, let us say that these are the different phase diagrams that are possible, and these are the different alloys that are possible. So when you take two entities, there can be existence in when terms of solubility in the liquid phase or in the solid phase, and there can be complete solubility, partial soluble, or completely insoluble. So that's what is being discussed here. So let us take the first example itself, that is isomorphous system, wherein two components are completely soluble in the liquid state as well as in the solid state. So before we understand this, you need to know that when we have any phase diagram, you should start with a uh, pure and also for the alloy type. So let me go to a plain blank sheet and then okay, so let us look at this figure here. And you can see when we plot a cooling curve between pure metal, that is time versus temperature, then this is how the pattern is. That means as time progresses, slowly the trend of temperature is gradually decreasing, and then there will reach a point which is called as a freezing temperature, wherein the liquid will freezes to solid, and this is that temperature for, let's say, for some element A, since it is a pure metal, and this is constant. That means for a single element, pure metal, you'll have a constant temperature at which the liquid will transform into solid, and this is how it will be taking certain time for conversion, but it will happen at a constant temperature, wherein this liquid will transform into a solid, and we represent the solid in terms of a Greek letter like alpha, beta, gamma, and so on and so forth. So this is how the pure metal cooling curve will look like. Whereas when it comes to an alloy, you can see this cooling curve will have two elements. So let's say certain amount of composition, let's say A50, B50 or A30, B70, so on. So there will be an observation of twice the change in the slope. This is the first indication of change in slope, and this is the second indication, which is nothing but this is the beginning of transformation, and it is first starts to transform or first starts to solidify, and the end of solidification takes place here, and below this entirely completely solid. That is nothing but above this there is a liquid phase, and below this there is a solid phase, and in between you have a two phase region of both solid in A and B. So this is what we understand with the which is an example for pure metal cooling curve and the alloy phase cooling curve. So when we go back and try to understand the relationship. So let us take the first example, which is nothing but isomorphous system, wherein two components are completely soluble in both liquid and in the solid state. So like I was discussing, when it is a pure metal, we have a horizontal line. When it is an alloy, it is an alloy. So you have two elements. So there will be in the cooling curve twice the change. So when I'm trying to plot the phase diagram, what I'll try to do is on the x-axis, I'll take all the possible combinations or all the possibilities that it can exist. Let's say, for example, for a generic way, two components are completely soluble in liquid and in the solid state. So I'll take all the possibilities wherein on the x-axis starting point, we take A0, B100, and then I keep on increasing up to B0 and A100. So let's say if the first one is uh, A is 100. What does it mean? A 100 means 100% A, which is nothing but pure A. On the other extreme, when I say B is 100%, that means this is where B is pure, and this is like a pure metal. So obviously, when it is a pure metal, like we discussed in the previous slide, cooling curve, it will have a horizontal line. So that's why it is shown as a horizontal line. And all in between A and B pure entities, you have an alloy wherein it may be in a steps of 1, 5, 10, so on and so forth. If you keep it very close to 0, you'll have a very good curvature. It only takes a number of experiments to plot this, and it gives a very neat curvature. That's all. But let us take in 20 steps, like B20, A80, B20, and the next one will be A60, B40, or A40, B60, and A20, B80, and then finally A0, B100. So in all these cases, you have twice the change in slope, that is an alloy. So this is the beginning of solidification, and this is the ending of solidification, so on. So when this is how we construct any phase diagram. So since this is a isomorphous system wherein two components are completely soluble in the liquid state and solid phase, you got this type of phase diagram. But if it is a different one, you will get a altogether different type. It is nothing that you always may end up getting the similar type of phase diagram. So this is when I join locus of all the points which mark the beginning of solidification. You may be wondering where is the beginning and ending for pure metals. For pure metals, since the transformation takes place directly at a constant temperature, liquid will solidify to solid. So this itself will mark as the both beginning and ending of transformation. So it starts here. So when I plot all the beginning of transformation, so locus of all the points which mark the beginning of solidification, this is called Liquidus line. So this is the line which separates the liquid to solid, since this is the beginning of solidification, above which everything will be in the liquid state. Then I join locus of all the points which mark the end of solidification. So this is the locus of points which mark the end of solidification, below which everything will be in the solid state. So this is the Solidus line. So this is only used for the determination of or construction of a phase diagram, but every time we need not use the constructional one. Once it is understood, we only plot the outline. And we are going to take one individual case about how it is going to vary from the liquid state to two-phase region, liquid plus solid, and solid phase below the Liquidus line. We are going to take one example, and then we are also going to determine how it is going to transform. So if you can recall, we are going to understand that the mechanism of crystallization will start with liquid metal, and then the nuclei formation, and slowly it grows into dendrite. Dendrite will grow into grain, and then finally the grain boundaries also will be combining and forming the complete grain structure. Anyway, we are going to see and also try to use a rule which will help us to determine what is the amount of liquid and solid present in the two phase regions and so on. So this is about the isomorphous system wherein two components are completely soluble in the liquid state and in the solid state. So that's all for this video. Let's have another video wherein we can discuss about the other types of phase diagrams. So thank you. Happy learning.